Okay, let's look at an example of an op-amp, or pardon me, a circuit that has multiple op-amps. And in this case, I've got a circuit here that has 2 op-amps. We want to look how to analyze this type of circuit. So what kind of approach should we do if a circuit has more than 1 op-amp? Well, the 3 rules still apply. We just have to make sure we apply them properly to both these op-amps. So our 3 rules of analysis. First of all, Vn is equal to Vp for each op-amp. However, that doesn't mean they all have the same voltage. It means each op-amp, Vp is equal to Vn for that op-amp. They're the same voltage. But that doesn't mean that these 2 voltages are the same as those 2 voltages. So different op-amps will have different Vn equal Vp values. And of course, rule number 1 assumes negative feedback. Which of course is certainly the case here. I've got a path from the output to the inverting input for both of those op-amps in this circuit. Rule number 2. In is equal to Ip is equal to 0 for all op-amps. And rule number 3, never write a KCL equation at any op-amp output unless you need to know the current that is flowing out of the op-amp. So unless you want to find that output current, as with any defined node, you don't need that. So these 3 rules we're familiar with. Let's go ahead and let's apply them to this circuit, and let's see if we can get an expression for V out in terms of the voltage Vn. So in this case, first of all, we know our input currents are equal to 0. We also know that Vp is equal to Vn, which means if I have 0 volts here, I must have 0 volts here. And I'm going to give a name to this node. I'm going to call this node VO1. It's the output of the first op-amp. And if I've got voltage VO1 here, I don't know what that is yet, but I know I must also have it over here on the other input. And now that I know that, I can go through and write KCL equations. So the only nodes I can actually write a KCL equation for are this node. Can't write one for that. That's the output of an op-amp. I can write one for that node. Cannot write the KCL equation for that. Again, that's the output of an op-amp. So really there are only 2 nodal equations I can write. And if I write those, what I'll get is, for this node, Vn minus 0 over R1 is equal to 0 minus VO1 over R2. And if I do a little bit of algebra to this, what I will get is that VO1 is equal to minus R2 over R1 times Vn. And you will note this is nothing more than the inverting op-amp equation. And really, if you cover that part up, you can see, yeah, that's nothing but the inverting amplifier. Nothing more. So Now let's write the KCL equation for this node. So for that one, VO1 over R4 flowing out must be equal to V out minus VO1 over R3. And once again, if I do a little bit of arrangement, what I will get is that V out is equal to 1 plus R3 over R4 times VO1. And looking at this, that's actually just the non-inverting amplifier equation, which in fact, if you look at this, and VO1's at that input, once again, you've seen that before. Of course, the load resistors RL1 and RL2 have no effect on the KCL. Well, once you've got these, you can substitute VO1 into this equation. If we substitute VO1, what we will get is that V out will be equal to 1 plus R3 over R4 times minus R2 over R1 times Vn. And there's our result. So nothing really different from analyzing a single op amp. We just have to apply the 3 rules properly. Other than that, you have to write the KCL and you should be done. Well, there are lots of different applications you can do with multiple op amps, but let me show you one very popular application for multiple op amp circuits. And you'll see this used throughout, for example, biomedical and mechanical engineering as well as electrical engineering. This particular type of circuit configuration is used in all types of sensors, for example. And that particular circuit is called the instrumentation amplifier. Let's look at that for a moment. Let's consider what an instrumentation amplifier is. And in order to understand why we build something called an instrumentation amplifier, I first want to show you the purpose behind it, or why this particular configuration is used. Let's recall a circuit we looked at before, the difference amplifier. And I'll just re-sketch that one very quickly. So if I've got an instrumentation amplifier, and notice I've got the same resistor values, R2, R2, R1, R1. And if you take this and actually go through and do the calculation we did before, what you'll get is that VO is equal to R2 over R1 times V2 minus V1. So we saw this equation before. This is a really useful circuit because it allows us to look at the difference between two input signals, and that is very important to trying to measure signals like biomedical signals, heartbeat, EKG, ECG signals, or any type of very sensitive signal. You look at the difference between two signals and try to get out that very tiny difference between the two of them. So you see this used a great deal in engineering, but the difference amplifier is not really a very good way of implementing this function. It's got two drawbacks. First of all, drawback number one. If you want to change the gain value, you have to change two resistors at once. in order to make this ratio work. So if you want to go, from one value to another, you've either got to change both R1s or both R2s. So two resistors have to be adjusted, and they have to be very closely matched in value for this circuit to work properly. So if we want to alter the gain, we need to change two resistors, which is, it's doable, but it's really not very, how should I say, it's really not very elegant. There's another bigger problem as well. You've got non-zero input currents flowing into the input of this difference amplifier. Now, I'm not saying that the inputs to the op amp are non-zero. Those, of course, are zero, right? These two currents going into the input of the op amp. But the current flowing through these resistors is going to be non-zero. You can prove that with KCl. What that means is the difference amplifier will load anything it's connected to. You have a loading effect because it draws current from any circuit you connect it to. So a difference amplifier, it works. It certainly does implement this particular mathematical function, but it really has some drawbacks that make it kind of difficult to use. Is there a better way? Is there a better way to implement this function? Well, there is if you're willing to use more op amps, and that's where the instrumentation amplifier comes in. Here's a better way to do the difference function. Okay, and I notice in this case my V1 and V2 inputs are now going into two separate op amps. All of these resistors have the same value. They all have a value of R. These resistors have a value of R. This resistor, R sub G. So I've got three op amps combined together with now my inputs going into those two separate amplifiers. Let's apply the three rules and go through and let's analyze this circuit and let's see how it works. Okay. First of all, I'm going to give some voltage names to the output nodes for these op amps. I'll call this V3, call that V4. And now, call this, okay, if I look at this, if I've got V1 here and I've got a virtual short circuit, clearly I've got to have V1 there. I've got V2 here, once again a virtual short circuit. I need to have V2 here. So V2, V2, V1, V1. So the virtual short circuit sets up these voltages. I also note that the currents are equal to 0 flowing into these op amps, which means that all three of these currents have to be the same current. If I've got 0 flowing out of that node by KCL, each of these must be the same. So in this case, we can go through and we can write some KCL equations. So for my node here, what I've got is that V3 minus V1 over R must be equal to V1 minus V2 over RG. And if I do a little bit of rearranging of terms, what I will get is that V3 is equal to R over RG times V1 minus V2 plus V1. So I just took this and did a little bit of algebra to get that result. Now for this node, what I have is that V1 minus V2 over RG must be equal to V2 minus V4 over R. Once again, I can do a little rearranging of terms. And what I get is that V4 is equal to R over RG times V2 minus V1 plus V2. So looking at this, I've got expressions now for V3 and V4 in terms of V1 and V2. Now let's look at the rest of this circuit, okay? And what you want to do is look at the circuit we just thought about a moment ago. We looked at the difference amplifier. I'm going to divide this. If I partition this circuit like so, obviously I've got V3 here and V4 here. What is that circuit? That's just a difference amplifier. So this portion here, I can easily prove to myself that for here, VO must be equal to R over R, since all those resistors are the same, times V4 minus V3 is just equal to V4 minus V3. So I've got this. Now I've got these two. Let's substitute V3 and V4 into that expression. And if we do that, what we will get is that VO is equal to R over RG times V2 minus V1 plus V2 minus V1 plus V2 minus V1. And if I go through and combine terms together, what I'm going to get is this is equal to 2 times R divided by RG plus 1 times V2 minus V1. And that's our expression. So here's our expression for our instrumentation amplifier output voltage. Now notice what we have here. Clearly this is a difference amplifier function. I've got a gain term multiplied times V2 minus V1. But there are some differences. First of all, the input currents are equal to 0, so we have no loading by the instrumentation amplifier. Zero input currents, no loading effect, which means I can connect these inputs without it affecting the circuit I'm trying to measure. Secondly, let's look at this term here. If I want to change the gain of this amplifier, how can I do that? Well, notice RG can be increased or decreased to change the gain. I really only need to change one resistor, R sub G, in order to change the gain. So, two big advantages now compared to what we had before. No more loading effect, and now I can adjust the gain by changing the value of a single resistor. In fact, what you'll typically find is this. For an instrumentation amplifier, normally all of these components will be packaged together. So the op amps and all of the R value resistors will all be placed inside one single package. You'll have two pins sticking out of the package where you can connect a resistor, RG, and that single resistor sets your gain. So this is very typical if you want to adjust the gain, this kind of bundling all of the elements together, because you can manufacture them and you can ensure that all of these resistor values are very closely matched to each other. So this is a very, very common circuit. In fact, you can find literally hundreds of different op-amp commercial instrumentation amplifiers based on op-amps. You can find those sold by numerous manufacturers. Very commonly used circuit. So, I mean, this is of course just one of many examples of a multi-op-amp circuit, but it's an extremely useful one and one that has a great deal of application in all types of fields of engineering. Okay? So, next time we'll finish up op-amps by looking at what we call saturation. What happens, and we mentioned this before, if we try to make the output voltage exceed the power supply rails? Because remember we said before you can't do that. But what happens if we try to make that happen? We'll look at that next time, and we'll also look at a very interesting application of a circuit that does not use negative feedback.